All right, we are going to look at 50 chemistry questions you should know how to answer, and we're going to look at one. Okay, so section 1. So we're going to skip the bold parts and just focus on the questions. How many protons are there in a nucleus of Kr85? Well, by definition, the number of protons is equal to the atomic number, so that's all I need. The atomic number of Kr is 36 protons. What is the nuclear charge of an atom of Br? Well, here's what you should remember. So here's a nucleus, okay? Inside the nucleus, we have something called nucleons. All right, nucleons are two, either protons or neutrons, because we have electrons here in the electron cloud in the orbitals. Protons have a positive charge and neutrons have no charge. So that means the nucleus has two sets of nucleons, but only one nucleon has a charge. So no matter what, the nucleus is going to be positive. It's going to be positive how many? Positive how many protons there are. So bromine has an atomic number of 35, so it's going to have a positive 35 charge on its nucleus. And what is the mass of the protons in a nucleus of O15? That's oxygen 15. Well, the mass of a proton is 1 atomic mass unit. Remember, here in table D is where we have the unit right here. And so what do we need to know? Well, the mass of the protons would be, what is the atomic number of oxygen? 8. So 8 protons has a mass of 8 atomic mass units. How many neutrons are there in this nucleus? Well, we'd have to take the top number minus the bottom number. Remember, in reality, these should be directly above each other, just hard printed. So I would take 56 minus 26. That gives me 30 neutrons. Next one is asking about isotopes. Isotopes have the same protons, but a different number of neutrons. Same atomic number, different mass number. So it's the same element because it has the same number of protons, but just a different mass number, a different number of neutrons. So the two isotopes would be those. Which particle has a mass that is 1 over 1/836 the mass of a proton? So smaller than a proton, like really small, almost 1/2000th, which is the number that we looked at. And that's an electron. So how do I know which one of those is an electron? Well, you kind of have to remember it, but also table O can help you. A beta particle is an electron. So it's going to be this one. All right, so now we have to write some equations, and we're going to write decay equations. So we're looking at table N. All right, so in table N, I need uranium-238. That is this decay. Then I need K37, B plus, and P32, B minus. Okay, so what do I do with that? Well, I start building my equation. U238, K37, P32. So natural decay means it just starts with one thing and then it decays. The one thing I know it makes in this case is this particle. So go back here. What does this? This is table O. So I'm going to write this. 4,2He plus something else. I don't know what yet. K37 was B plus. So let's look at what that is. Okay, so I'm going to write this. 0 plus 1. And then P32 was B minus, which is right here. So I'm going to write that. Okay. Now I need to find what's missing. Okay. So I can do the top easy. 238 equals 4 plus something. So 238 equals 4 plus something. Okay, that should be easy math, right? 234. Now, how do I figure out the bottom number? Well, I'm going to have to go to my periodic table, and here's why. Look up uranium, and what is its atomic number? 92. Let's look up the other ones just while we're here. K is 19. And phosphorus is 15. Okay. So now I can figure out the bottom number. 92 equals 2 plus something. Well, that would be 90, right? So 90 plus 2 equals 92. Now look up 90. TH. 37, it's a 0 up there. Well, that's easy math, right? Now down here, 19 equals 1 plus, okay, that would be 18. Let's check it. 18 plus 1 is 19. Yes. What's the atomic number? 18. Argon. And then P, 32 on the top. 0, so still 32, because 32 plus 0 is 32. On the bottom, we have to be careful because we have a negative. Something plus negative 1 is 15. So it's actually going to be 16. And then I need to look that up, and that is S. Okay, down here, types of nuclear reactions. So I'm going to do easy one first, fusion. Fusion means taking two little itty bitty nuclei and smushing them together and making a big one. Here we go, number 4. Another easy one is natural decay. So that means just like these all had one reactant and it just falls apart. It's like that. Okay, so that is clearly number 3. Okay, fission is where we take a nucleus, hit it with something, and it breaks apart. Okay, so take a big nucleus, hit it with something, and see how it breaks apart to 2 different elements, lots of smaller pieces. Okay, and then artificial transmutation would be left. And technically, this is definitely always natural decay. And these are all artificial transmutations. Okay, but it wouldn't never be asked like this. It would be which one is natural, which one is artificial, or which one is fission, or which one is fusion. Okay, it wouldn't be asked in this way, so just be careful. All right, now we're going to do atomic mass. Okay, and we have to do it using some calculations. So I have this atomic mass, and I have this atomic mass, and I have 2%. So what I'm going to do is take 50 atomic mass units, 52 atomic mass units. The 52 goes with 80%, but I need to change it to a decimal. Change this one to a decimal because that was 20%. Okay, now do the math. So 50.0 times 0.200 equals 10. And then 52.0 times 0.800 equals 41.6. Now, before I go any further, what I should get is an answer between 50 and 52, but closer to 52 because 52 is 80% of all the atoms. Okay, so now I add these two numbers up and I get 51.6 U as my answer. And yes, it is between 50 and 52, and yes, it is closer to 52. Now, what if the question asked you, I want you to tell me what element that is? So what you'd have to do is look at atomic masses, right? And so this is 51, this is 52, basically, this is 55. So technically it would be closest to this, but if you were asked this question, it would be much closer than this example I'm giving you. So, but that is how you would find it, okay? Now, before we do this question, I just need to make an adjustment to this time. So just give me a second, because this actually used the old reference tables, and things kind of got changed a little bit after that. So this should actually be 15.813 years. Okay, that'll make more sense when we do the problem. Okay. So a sample of cobalt-60 is left to sit for this many years. How many half-lives have gone by? So what I do is I go to the reference table, I look up the half-life of cobalt-60, and it is 5.271 years. If it took this long, I would take this number divided by this, and that'll tell me the number of half-lives. Or you could do it like if I had 2 half-lives, it would be 5.271 plus 5.271, which wouldn't get me to 15 yet. So I'd have to do it 3. So this divided by this is 3 half-lives. What percent of the original sample remains after this number of half-lives? Well, we start with 100%, then we go to 50%, 1 half-life. 25%, 2 half-lives. 12.5%, 3 half-lives. If the original mass was 20 grams, how much would be left? Well, we'd go 10 grams, 1 half-life. 5 grams, 2 half-lives. 2.5 grams, 3 half-lives. Okay? And that is the end of section 1.